Okay, and on the other side of the planet, Curiosity has broken the 2,000-day mark by about 2 months ago. I think we talked about that. So today is day 2067 for Curiosity. And the location there is the inside of Gale Crater. This is about a 150 kilometer diameter impact crater. This is the location of was the targeted landing area. They landed more or less in the middle of it. And right in the center of the crater is a mound of layered sedimentary rock called Mount Sharp. That's about 5 kilometers of relief, so roughly 18,000 feet or so of layered rocks. And this is what Mount Sharp looked like shortly after landing when they turned the cameras toward it. And they're actually over in this area poised to start roving up the foothills of Mount Sharp. And this is a little bit closer view. You can see all these wonderful layers. And the purpose of this mission is to examine the stratigraphy, if you will. The oldest layers are on the bottom. As you move upslope, you get to younger and younger layers of rock. They have instruments on board that they can collect samples and determine the composition of the rocks, the mineralogy, and the environment that the rocks were formed in. And so by having, starting at the bottom and moving up, you're basically turning the history book forward. You're seeing what the environment was like early on and then how it's changed with time. So this is an overhead view of their path so far. So they landed up here. Mount Sharp is down here. These dark areas are very thick sand dunes, and so they've been skirting the sand dunes until they found an opening in them, and now this is where their target is. At this point, they're in this general area. They've been examining this ridge, which is called Vera Rubin, and this ridge has a lot of hematite in it. So again, it's good evidence that there was water at the time that ridge was formed. And so I'm going to zoom in. This is where they were about a month ago, where that green X was. This is just another view of this, showing all of the different locations. Every place they've got a name for a target, that's where they stopped and examined a rock or bedrock or features, whatever. So there's been lots of stops along the way. And so this is a closer up view. This is the top of the ridge. It's about 10 meters or so, so say 35 to 40 feet of elevation difference between down here and the top of the ridge. And so they've actually climbed up onto the top of the ridge and been going around examining the rocks. And so here's where we were last month when we got together, and here's where we are now. So last month they were about right here, and so they've actually climbed back down off of the ridge and have been looking for particular targets. So they've found an area that they think is the basic layer of material that lies just under the Vera Rubin area. So they've done lots of studies on the top of that, and now they're looking at what came just before it. And I wanted to backpedal for a couple minutes. I think in March we looked at this process they've been going through. In late 2016, the drill on board developed a problem. And without the drill, they really have limited capabilities to collect samples and actually get the detailed measurements thereafter. And so I think I have a video here describing what the problem was and how they've been attempting to correct that.
Since Curiosity landed on Mars in 2012, it's used its drill to acquire samples from Martian rocks 15 times. But a little over a year ago, in December of 2016, Curiosity's drill started giving it problems. The drill's feed mechanism, which is responsible for moving Curiosity's drill bit into and out of rocks, didn't move when commanded. When Curiosity drills into a rock the way it was designed to, the drill's 2 stabilizer posts touch the rock first to steady the arm while the drill's feed mechanism moves the bit forward into the rock. Without the feed mechanism working, we can't drill that way. To solve this problem, we do what we always do. We worked it out in the test bed using Curiosity's twin on Earth. Our team of engineers and scientists have been working for months to figure out a way to collect and deliver rock samples without using the feed mechanism. Here's what we came up with. Using our new technique called feed extended drilling, the stabilizers are not used. The bit is now in a forward position extended past the stabilizers. Moving the drill straight into a rock and retracting safely without the stabilizers is challenging. We move the arm instead of the feed mechanism to place the bit onto the rock and press it forward as it drills. After making contact, we apply a light preload and drill a shallow pilot hole. We use a force sensor in the robotic arm to give Curiosity a sense of touch. This lets Curiosity adjust its arm motion and avoid getting stuck while drilling, kind of like you might adjust your arm while drilling into a wall at home. After drilling, we use a similar technique to retract from the hole without getting stuck. We recently tried this method using Curiosity on Mars, and here's how it turned out. This picture shows the first hole drilled on Mars ever with this new drilling technique. Even though we can't see the hole in this image, we know we drilled about 1 centimeter deep. The hole itself is buried under the powder generated during drilling. This is a good sign for the new drilling method. Next, we have to drill a deeper hole to collect sample and demonstrate our new techniques for delivering the sample to Curiosity's 2 onboard labs. That will come in the days ahead.
Okay, so that's where they were in late February, early March. And the next video is some testing they've been doing where they actually were drilling holes in the rocks. And so you can, and this will repeat, and see how they use the arm to push the entire assembly down. And so they've finally been ready to try this with Curiosity on Mars. And there's a couple things to pay attention to here. One is, first of all, they're very concerned about using the arm in this way because they're actually applying a fair amount of force to push it, to push the drill down, and they're very wary of doing anything to damage any of the joints on the arm. And so that's one reason why it's taken so long. The second aspect of this is the drill bit acts as sort of an auger. And so as it's drilling in, there's a little bit of material that sort of goes up into the drill fixture. And so that's what they're relying on now to actually collect the sample that they need. Previously, they had a little sample scoop that was like a couple of tablespoons big. They'd come along and scoop that up, and then they'd be able to sieve the material. And they're not doing that, so what they need to do is use this auger to collect a little bit of the powdered rock, take it over to where the instruments are, and then reverse the drill so it releases some of the material. And so here's what the results are. So this is earlier in the month. First, they came up on this rock and just brushed the dust off of it. So that's what they typically do. And then this was the area that they chose to try drilling. And so here's a close-up of the drill. There's the drill bit extended there. And there we go with their first successful drill hole using this new technique. And that's about 5 centimeters deep, so roughly 2 inches or so. And just for scale, that's about like a nickel in diameter. So, and there's this powdered material piled up around it. And so this is a little closer view of that. And then the next view is from the ChemCam, which is the laser experiment where they can actually zap the surface with a high-powered laser and vaporize the rock and determine that way sort of the gross chemistry of the rock. And so this is the telescope on the ChemCam looking at the drill hole. And they actually, subsequent to this image, came along and zapped several spots inside the drill hole, and so they were able to get an estimate of what the subsurface composition of the rock was. And so the next thing they did was wanted to see how much material they could actually deliver to the onboard instruments. And each instrument has a little door on it that's hinged, and so these are 2 of those doors. And they put the drill above that and reversed the motion of it and tried to dump some material on it. This is a little bit closer view. And the analysis of this says that that is not enough sample to actually do a valid experiment with. And so rather than dirty this even more than they already have, they're experimenting just with dumping sample on the surface and then seeing if they can estimate how much material they've got there. So they've done the same thing here. You can see a little bit of material there, a little bit of material here, and that's still not enough. And so that's what they're concentrating on now, is to drill another hole and collect more sample and try to increase the amount of material that they're pulling up into this auger mechanism. And so this is the most recent image taken just, I think, a day ago. And I'd mentioned that it's the dusty season on Mars, the southern hemisphere summer, and this is when dust storms typically are brewing up across the planet. And so this is looking at the far crater rim of Gale crater, and you can see, up close, it's fairly clear. The farther away you get, the dustier it gets and the hazier it appears. And so we'll be keeping an eye on that. The good thing for Curiosity is it's powered by plutonium, so it doesn't have to worry about dust reducing the power output of its power system. Okay, so the recap for Curiosity, it's day 2067 since landing. They've driven about 19 kilometers, and I expect by the time we get together next month, we will have broken 500,000 images returned. So it's definitely got lots of photo ops as it's driving around.